Now we go on to design an op-amp, design a differential amplifier. Design an instrumentation amplifier. Requirements. 1. Common mode rejection ratio must be greater than or equal to 87.96 dB. From earlier part of question. Resistor matching is challenging because to get approximately 88 dB is very difficult to match resistors to that. 60 dB is 0.1%, so 87.96, 88 dB is very impossible. So place all gain, that's times 200 because we've got that from part E earlier. The diff equals 2 times RA plus RB over RB times 1, which is R over R from the difference stage. And now we need to fix some resistor values. So let RB equal 100 ohms. It can be any value at all. We just have to make a guesstimate for that. Therefore, RA equals 9950 ohms. And by putting all gain in input stage, we can relax the tolerances on difference amplifier, which is the second stage. So our overall common mode rejection ratio equals 87.96 dB. Minus AV, which equals times 200, which is 46.02 dB, equals 41.94 dB. So the difference amplifier common mode rejection ratio equals 41.94 dB. The common mode gain of the diff amplifier, ACM, equals delta over R, and delta equals 2 times tolerance. So 41.94 dB is approximately 1 over 125, which equals 0.8%, which equals delta, 2 times tolerance. Therefore, diff amp resistors must be less than or equal to 0.4% tolerance. And this figure here is actually slightly tougher to meet than the figure we calculated out in part E. So it's tougher to meet than part E. And we must have this to get the common mode rejection ratio. So we can slightly relax the tolerances for RA and RB, because if total error equals 2.9%, then can allow RA plus RB to equal 2.9% minus 0.8%, which is approximately 2.1%. Which is approximately 0.7% for RA, RB, and RE. Remember, you've got two RAs here, and they're separate resistors, so you still have the combination of both. Final resistor choice, RA equals 9950, RB equals, what was it, 100 ohms, and R for the diff amp, anywhere between 1 k ohm to 20 k ohms. And that's up to you, that's your choice. If you go higher than 20 k ohms, you know from your other studies that you'll get lots of noise. And if you're much lower than 1 k ohm, you also know that you may land up not being able to drive the lower value from the amplifiers. So anywhere between 1 k ohm and 20 k ohms is absolutely fine for this. And the final part, and I should say that this question is longer than and more complex than you would normally get in an exam, because this exam in 2017 had 3 questions and you will have 4, so they're slightly smaller. And it talks about if you design the circuit in part F and it's been optimized to drive the production test equipment, in other words, the 1 volt RMS, consider the worst case peak signals appearing at the output of the cartridge, combined with an audio band covering 20 hertz to 20 kilohertz, and describe any limitations this circuit might have when playing vinyl records. So this last part is worth 7 marks. I think that was 7 out of 25 or 30, I can't remember. And the challenge that you're being asked here is you need to think about what problems this circuit would have in practice and how might you solve them. So you've calculated out that you've got a limited supply voltage, or you've been told you have a limited supply voltage. Supply voltage equals plus and minus 5 volts. Peak signal equals 90 micrometers, which goes to 56 millivolts peak. Gain equals times 200 would go to 56 millivolts times 200, which would equal, it says here, 11 volts. So solution 1, increase the power supply. 2, say plus or minus 12 volts, 15 volts. 2, reduce the gain. If you cannot increase the supplies. And the final part, which I would not set again, it was actually too complex, was that it talked about the frequency response, and it required you to recognize that the series inductance would actually have a significant effect above 1 kilohertz for the circuit. But I would not set that style of question again. It was too complex for the students, and I don't think anybody got that last part. But the power supply one is a perfectly reasonable one. It basically says, take the circuit as you've been defined. You've been told that a peak signal has got to be reproduced at 90 micrometers, which would give you 56 millivolts peak into the input. The gain is defined as 200 times, so you'd land up with plus or minus 11 volts peak coming out the output. So you either have to reduce the gain down from 200 or increase the power supplies. And given that the circuit is actually being optimized to drive this test equipment, the obvious solution is to change the power supplies. So that there completes that question.